for the number families, they have a special symbol for each of them. Maybe I'll write the special symbol right beside it. It's got a double line. That one we use not very much. The ones that you're going to find used the most are the integers and the and the real numbers. But your natural numbers, those started off with counting numbers. Those are the very first numbers historically that people came to because they wanted to count things. And then the whole numbers include all of the natural numbers, and the only thing new is they add the 0. So this is where when you were trying to group them, it made it a little bit difficult because if you wanted to use what mathematicians did, the numbers fall into more than one category. So the number 2 is a natural number, but it's also a whole number as well. It falls into both of those. The smallest grouping it's in is the natural numbers. Then we get to our integers, and as you get into higher level math, the symbol is a Z, and that Z comes from the German word Zahlen, which means number. But integers include all of the whole numbers, see the 0, 1, 2, 3, but then includes the negative numbers. So we have, in certain things, we need to include negative numbers for different types of math. Like when you talk about temperature, sometimes in winter the temperature goes to -15, then you have a negative number involved there. We use the letter Q. You can think of quotient for any rational number, and that's every number that can be expressed as a fraction of integers. So when we think of the word quotient, quotient is dividing. This is an example of a rational number. But so is the number 2, because the number 2 you could write as 2 over 1. So anything that you can write as a fraction using positive or negative numbers, so -3 would also be a rational number. Any fraction whatsoever is a rational number. Now, this includes every decimal that terminates or repeats. Okay? So if you had 3.218, this is the same as 3 as a mixed fraction, 3 and 208 thousandths, because this is your, right, if we want to change a decimal into a fraction, I guess I should put tenths, hundredths, thousandths. If I go to the 8, which is in thousand, I can write that fraction as 218 over 1,000. Of course, I could reduce that if I wanted to, but I'm just going to leave it like this right now, because it means that any decimal that ends, that tells us that you can write it as a fraction. But we also have in here decimals that repeat. So decimal that repeats, have you ever seen this notation? Sometimes they draw it like this. I've also seen sometimes they put a dot over top to say that that 2 keeps on going forever. Take out your calculator if you've brought it and check this out. This is kind of cool. That if you do 2 divided by 9, you get 2's that repeat forever. And this starts a pattern for repeating decimals. So for example, I'm going to get excited about repeating decimals because I think it's pretty cool. Okay, so if you have 2 numbers repeating, like 0.18, this is like 0.181818 forever. It's equal to this this fraction. Type that into your calculator. 18 divided by 99. And you get 0.1818118. So a pattern is starting to happen here. What do you think 0.327 repeated would be as a fraction? Check it out. Try it on your calculator. Is 327 divided by 999 0.327? Very cool. And then, so what you can do is, this is where it gets a little bit fun. Let's say I had something like this. 3, 2, 5, 7, but the 5, 7 only started there. How would we do that? Well, I know that 5, 7 over 99 is 0.57 repeated, right? So how can I move that 57 2 decimal places over? Well, if I divide it by 10, I'd move it once. If I divide it by 100, I'd move it twice. Try this out. I'm curious. I'm playing around with numbers. Is this equal to that? Does it work? Is it 0.005757575757? There's an 8 at the end of the last one because your calculator saw the 7 and said the next number is a 5, so they rounded up. Does that make sense? Okay. So that means if we wanted to take this, the 30.32 is 32 over 100 plus 57 over 9900. That should change that, and you can add fractions by getting a common denominator. For those of you that have a graphing calculator, I'm going to show you something kind of cool. So I have 32 divided by 100 plus, and then I had 57 divided by 9900. Enter that, and I got 0.3257575757, and there's an 8 at the end because it rounded. But on the graphing calculator, if you hit your math button, and then number 1 says change it to a fraction, it tells me that this fraction happens to be 43 over 132. I think it's kind of cool that the calculator can do that. It'll also always put it in lowest terms for you. Now what I'm doing right now is I'm just trying to show you that every number that can be represented as a fraction is a rational number. And that you have to sometimes recognize if you have decimals that either end, because if they stop, you can just say, hey, that's my thousands, and I can make a fraction with the thousands. Or if they repeat, and the repeating thing is really kind of cool because it always has something to do with a 9. I mean, there are other things that repeat, like, did you know that 1/3 is 0.3 repeated? Which happens to also be 3/9. Makes sense as well. And then we get into numbers that don't belong to any of the other number families so far. These are our irrational numbers. So we write a cube, just like the rational numbers, but we put a bar over top of it. Sometimes there's a squiggle in front. That squiggle in front and that bar over top mathematically represents not rational. So irrational is, by definition, not a rational number. So then we have to have decimals that do not terminate or repeat. So things that never have a pattern that repeats itself. That includes many square roots. In fact, that's what our unit is right now. If you take your calculator and you take the square root of 2, you get 1.414, and you look at the numbers, and there's no pattern. And if you would go on to something, like sometimes you're like, oh, but I only see 8 decimals on my calculator, so I might want to check out, maybe my computer has can give me more decimal places. So I tell my computer to do the square root of 2, and there, I don't know if you can see, I've got a bunch of digits. I want to see more digits. Anything repeating yet? How about more? How about more? How about more? Look how many digits my computer can quickly get for me on the square root of 2. And if you try to study it to see if anything starts to repeat itself, any pattern, there is no pattern forever. Or is there? Because there could be numbers that have 1,000,000 digits that repeat themselves over and over again. So how do we tell if something is irrational? It gets a little bit difficult, okay? There's actually, once you get into higher level math, there's a very cool proof that proves that the square root of 2 is irrational, but it's a little bit complicated for grade 10 math, but you can look it up if you want. But the square root of 2 is an irrational number like many square roots. And then there are also some special numbers, like pi. Pi continues on forever without a pattern. Have you ever heard of the number e? It's like a weird, there's a number e, it's on your calculator somewhere. See if you can find the number e on your calculator, push enter, and get 2.718. You're going to study that number starting next year in grade 12 pre-calculus.
Next year, grade 12?
Yeah, because the plan is if you're in pre-calculus, you take grade 10 first semester, you take grade 11 second semester, and you'll be in grade 12 pre-calculus next year. And then you'll be in AP calculus after that. Holy cow, you guys are growing up so fast. Okay.
Are we just allowed to do grade 11 and grade 12 pre-cal without doing AP pre-cal and still graduate with our math?
You still can. Because to graduate from high school, you need a grade 12 math course. And there are 3 streams available. You can either have essentials, applied, or pre-calculus. If you are taking pre-calculus, the whole word of that course, pre-calculus, is because you are studying to do calculus. So if you are studying pre-calculus, it's probably because you want to go into some university program that requires calculus. So it makes sense, and students tend to do better if you take that already through AP calculus in high school. So the way that we plan it at our school is you do grade 10 pre-calculus and grade 11 pre-calculus in grade 10. That gives you grade 12 to do your grade 12 your grade 11 year to do your grade 12 pre-calculus. And then in grade 12, you take the AP calculus and the advanced math course, and you're super prepared for all of your university math courses. But if you're not planning on doing something that requires calculus in university, then you could choose to either take the applied math or the essentials math to graduate. All right. So there is, and the final group that we're going to talk about, and we use this symbol a lot, we're going to use it a lot this year as well, is all the families together. Sometimes there's a box around this to group this all together. All of your numbers together are called your real numbers. All of your rational numbers and all of your irrational numbers. The numbers that we don't talk about in high school are your complex numbers. And you had one on the piece of paper. You had the square root of -9 when you were cutting it out. If you type that into your calculator will probably give you some sort of answer that it's not a real answer. Non-real answer or error, because you're not allowed to take square roots in the real number system. You can, in the complex number system, there is an answer to this. It's 3i. And in the complex complex number system, they introduce one new number, and that new number is I, which is the square root of -1. So you could take some higher level complex number theory in university and learn about the number I and do square roots of negative numbers. But for our real number system, you can't do that. So that's one of the things that we don't understand. But now you can understand my poster over here. Makes a little bit more sense. Okay. So, take a look at these numbers. And I either want you to put the symbol of rational numbers or irrational. Whoa. So our rational number symbol is a Q, and our irrational number symbol is a Q with a line over top of it. And I'll give you a 30-second head start. All right, how did you do? First one is a rational number. Second one is an irrational number. Third one's a decimal. That stops. That's a rational number. Pi, very famous irrational number. 4/9 is a fraction. Fractions are easy. They're always rational numbers. Square root of 4 is equal to 2. That was tricky. Not all square roots are irrational numbers. And G, based on this one, I see no pattern. Okay? Based on the fact that there's no pattern yet, and it says ... that it keeps on going, we're going to assume this has no pattern. But this one has a ... and it does have a pattern. See how it goes 1, 3, 1, 3, 1, 3, and is repeating? That makes that one a rational number. Okay? Next, I'm going to put color code here. Make our symbol for natural numbers, whole numbers, integers, and rational numbers, and then I'll put off to the side irrational numbers, and all of these together make our, I need another color. That is really hard, that's bright. Real numbers. So many of these will have a lot of them, more than one. Give you a 30-second head start again. So the way that I wrote these is I wrote them in a line: natural, whole, integers, and real, irrational numbers, because if you have a natural number, you will have all of the ones underneath it as well. If you have a whole number, you'll have all of the ones underneath it as well, including r. In fact, unless one of these is a square root of a negative number, that's not possible. You will know that all of them will have the r. Wow. I'm getting my r bigger than I wanted. That's a little bit. So they'll all be real numbers. When I look at 44, is 44 a natural number? It is. And because it's a natural number, it'll also have the whole number, the integer, and the quotient. So there's going to be 5 families that the number 44 belongs to. Negative 3. Negative 3 is not a natural number. It's not a whole number, but it does include, it is an integer, which means underneath it, it will also include the rational numbers. 0 is not a natural number, but it is a whole number. And since it's a whole number, it'll include all of these ones underneath it as well. 5/9 is a fraction, but it's not an integer, not a whole number, not a natural number, so we can just add this one to real numbers. This number looking, does it have a pattern that repeats? No. And it continues forever. So we'll say it's irrational. Negative 2.3, that is a decimal that terminates, but it doesn't make it an integer, because integers are just positive, negative whole numbers. So this is all that we can add to that one. So sometimes it's nice, see how I wrote these in a column like that? If you have a natural number, you'll have all the ones underneath it. In fact, sometimes people put that r, here I'll extend, ooh, fancy. You can put the r underneath it, and same thing here, I can make a box here. But if your number isn't a square root of a negative, isn't something impossible, then it's always going to be a real number. Use a number line to estimate each of these numbers, and I want you to come up with an estimate first without a calculator, and then we'll do it with a calculator. So I'm going to write them all out here, 4 root 35, and then I'm going to have a column here for my estimate, and then I'm going to have an actual with our calculator. I'm going to write a column. Next one is 3 cube root of 18, square root of 7, cube root of 38, square root of 19, and finally the 4th root of 13. We're going to estimate first, and then we're going to go to our calculators and get an actual value, maybe to 3 decimal places. And then we're going to place them on our number line. Let's start with the square roots, because I think they're easier, the easiest ones to estimate. Okay? You know certain square roots. Certain square roots, certain perfect squares, you already know. Like you know the square root of 9 is 3. Square root of 4 is 2. So when I have the square root of 7, do you see that the square root is, this is fun for me too. You see that the square root of 7 is somewhere in between the square root of 4 and the square root of 9. Okay? So our estimate is it's going to be 2 point something. Because square root of 4 is 2 and square root of 9 is 3. How you estimate this now is there's like different strategies. Do you see that 7 is closer to the 9 than it is to the 4? So you might go higher than 2.5. You know, I've had other people say, I like to use this as an estimate, that this is a difference of 5 between 4 and 9, and we've gone 3 out of the 5 to get to 7. So some people would say, and since 3/5 is 0.6, I like 0.6 as an estimate. Okay? On an estimate, you will never lose marks for like something that's reasonable. Okay? So if you put 2.5, 2.6, or 2.7 here, they'd all probably be considered reasonable. If you put 2.1, you'd probably lose a half mark saying it's not that close to the 4. If you put 2.9, be like, it's not that close to the 9. So let's use that same strategy to see if we can figure out the square root of 19. What is the square root of 19 in between? Which perfect squares do you know? 16 and 25. So I know that it's going to be 4 point something. Seems like it's closer to the 16 than the 25. So if someone put 4.2 or 4.3, seems reasonable. If I count the difference between 16 and 25, that's a difference of 9. And I am 3/9 of the way along there. So that is about 0.3. We're going to see how close these are actually afterwards, but that's not a bad estimating strategy for square roots. So there's our square roots as far as estimates go. Let's do the cube roots next. The cube root of 18. And now you have to think of perfect cubes, because there are some cube roots that you know. Perfect cubes are when you multiply the same number by itself. Like 1 times 1 times 1 is a perfect cube. What is 2 times 2 times 2? 8. So you know that the cube root of 8 is 2. And if I do 3 times 3 times 3, I get 27. So you know that the cube root of 27 is 3. So when we go to estimate the cube root of 18, it's going to be 2 point something. Does 18 seem closer to 8 or closer to 27 or about right in the middle? I mean, this goes up by 10. This goes up by 9. Seems in the middle. We'll see how accurate 2.5 is as an estimate when we get our actual value. Okay? Because sometimes it's things like cube roots and fourth roots, they don't act perfectly in sync. So we'll see how that all results. What's the other cube root we have? We have cube root of 38. Seems like cube root of 27, which is 3, sorry. If 3 times 3 times 3 is 27, what's 4 times 4 times 4? So 38 is between 27 and 6 and 4. So the cube root of 38, I'm going to put at 3 point, seems quite a bit closer, it's only 11 away here, and it's almost, it's like 26 away here. So I think it's closer to this one. I don't know, I'm going to try 3.3. So some sort of, when you're estimating, you're giving some sort of guess based on where that number is. So that's all of our cube roots. Now we'll do our fourth roots. We'll start with the smaller one, which is the fourth root of 13. 1 times 1 times 1 times 1 is 1. What is 2 times 2 times 2 times 2? It's 16. So actually, 16, we actually have to include the fourth root of 1. And this is going to be 1 point something. And it seems like it's closer to this, well, it is closer to 16 than it is to 1, so I might go 1.8, maybe 1.7. And the next fourth root that we have is 35. So 2 times 2 times 2 times 2 is 16. What is 3 times 3 times 3 times 3? 81. This, I really like doing 3 times 3 times 3 times 3, because most students, when they do this, they do this. 3 times 3 is 9. 9 times 3, 27. 27 times 3, oh crap. And it takes you a while, and you get 81. Okay? But if you just do this and this, it's just 9 times 9, and that's a lot easier mental math. So we've got the fourth root of 81 is 3, and the fourth root of 16 is 2. So this is going to be 2 point something. It appears, what do we got here? It's about 20, and then about 40, or 46 here, and 19 here. So it seems like it's closer to the 2. So I'm going to put 2.3. So we've got all of our numbers there. And we go to our calculator. Now I know that most of you know where the square root button is. So we can go square root of 7. Is that one of them? And square root of 19. Is that the other one? Oh man. That would be exciting. So, good. And now back to my calculator. I've got 2.6 and 4.4 if I round. How did we do on our S? 2.6, and I'll put dots that it keeps on going, and 4.4. Oh, we did pretty good, right, in our estimates, not too bad. And this 4.3, look at that, it's 4.358, like, really, it was pretty close. Now let's go to our cube roots. On your calculator, you have a cube root button, but it's sometimes hard to see, okay? On the graphing calculator, you have to hit the math button to find the cube root. On your calculator, you'll need to find out where it is, okay? Calculators are wonderful, but as we get into higher level math, you have to find new buttons on there. If you haven't practiced with your own calculator, right? If you borrow one of mine and you're like, where's the button? I'm like, you should be using your own calculator. This is part of this class. Learning how to use a calculator is one thing. So if I go to the cube root and I want to do cube root of 18 and 38, so 18 and the cube root of 38, 2.6 and 3.4. How did we do? Okay, we did pretty good with the 3.3, and the 2.6 we were really close. I'm going to actually, see how these ones are really close? I'm going to add one more decimal for each of those. So this one was 2.62, and the other one was 2.65. 2.62, it's 2.65, rounded. It's actually 2.64. But those two are really close to each other. And then fourth roots on your calculator. Graphing calculator's under math. And they have this X button, saying that you can put any number in there that you like. Now depending on the calculator that you have, when I push it in, it lets me type in that number. Some calculators you have to push the 4 first and then type that in. Again, we need to make sure that we figure out how to do our calculator. So we want the fourth root of 13 was one of them, and the fourth root of 35. 1.9 and 2.4. We're really close with our estimate, and 2.4. And now that you have these, could you put them all on your number line? I'm pretty sure you could. So 1.9, right, would be right here. That one was the fourth root of 13. And our next one was 2.4. So at 2.4, we could switch colors. 2.4 would be right here. And that would be the fourth root of 35. And we could put the rest. We might decide that our scale isn't the greatest here because they're going to all get clumped in there. Okay, I'm sure you could do that. We're going to leave that for you to put the rest of them on the number line. I'll go dot, dot, dot. I'm pretty sure putting them on the number line would be fine. What might you do if this was your actual question? You might not include these negative numbers on your number line and make your number line a little bit wider so that you had more room to put things on. Okay, you've got a homework assignment there on page 211.